Okay, so sorry about that. So this week we're going to be talking about the atmosphere. We're going to be talking about specifically the terrestrial planets. And I forgot to hit record at the beginning, so you didn't see the what we talked about last week. But you can check out that video below. Hey, Andrew. So first I'm going to talk about just some basics of the atmosphere, because that's going to be relevant when we're talking about atmospheres around Mercury, Venus, the Moon, and Mars. And like I said before I remember to hit record, we're not going to worry about the Earth right now. So, yay, Dracorex, happy to have you. Yay. So some basics about the atmosphere. And the reason I remembered to hit record is because my parents watch this. And my dad's an atmospheric scientist, so no pressure. They're not watching it now, but they watch it on YouTube. So hi, Mom and Dad. All right, so some atmospheric basics. What is an atmosphere? Now, this is, again, one of those things that you ask people, and it's like, do you know what an atmosphere is? And everyone's like, duh. Yeah, of course I do. But there's specific definitions to them, and especially, I think this came up, I don't know if Andy's on, but Andy made this point in our Discord asking about the moon's atmosphere. And is there actually one? So we'll mention that. And it really comes from this definition. What is an atmosphere? And it's just a layer of gas that surrounds the world. It is shockingly thin. So 2/3 of the total air in our atmosphere on Earth are within just 10 kilometers of the surface. It just thins out a lot as you go up. And then the temperature typically, like especially for Earth, is low enough that these atoms can combine to form into molecules. So that's why if you hear about the fact that like we have a nitrogen-rich atmosphere, but it's more N2 or O2 or CO2, that's because the temperature of our planet is cold enough that those atoms can come together and form into molecules. To talk briefly about the thinness of the atmosphere. Hi, Brad. I like your coffee sandwich there. Coffee and soda sandwich. A good analogy for how thin our atmosphere is compared to the size of the Earth is if you can picture one of those just standard globes, you know, so about that big, the desk globes. Put a dollar bill on top of that, or a banknote, whatever you have. That's how thin the atmosphere is relative to the size of the Earth. So a globe with just one note on top of it. That's the thickness of our atmosphere relative to the size. So super, super thin, but very important. Atmospheric pressure is probably one of the most key components when it comes to studying atmospheres in astronomy, because it dictates a lot about, you know, the temperature, and particularly how liquid water can actually stay in liquid form on the surface. But this atmospheric pressure decreases as you go higher in altitude. And so, you know, I said up front at the top of this chart that within 10 kilometers of the Earth's surface is 2/3 of the air, and it thins out really, really fast. Again, that's something that we kind of understand, but just trying to wrap our head around how significant that actually is. So how atmospheres affect planets and why they're important. Lots of factors here. They create pressure that affects the liquid water, as I mentioned. They also absorb and scatter the light. So it's not just the fact that, you know, the atmosphere makes our sky blue, but the fact that it protects us from radiations because it absorbs and scatters. Remember when we talked about telescopes, and I'll show an image, I think on the next chart, about how far the different radiation gets into our atmosphere. That dictates where telescopes need to be. So if telescopes, you know, are more in the X-ray, they need to be outside of our atmosphere because our atmosphere absorbs X-ray radiation, which for us is a good thing. They create wind and weather and long-term climate of the planet, but particularly where we talked about the surface of the planets last week. Wind and weather dictate the surface of the planet. If you have an atmosphere, if there's wind and weather accompanying that, it's going to erode the surface, or it's just going to change the patterns of the surface. And then we get these interactions between gases and solar winds that can create a magnetosphere. So think more about the fact, like, this one's kind of hard to wrap our heads around, but think about the northern and southern lights. That's not strictly magnetosphere definition, but this is kind of the same phenomenon. That solar wind hits our magnetic field. Okay, that's a separate thing. But that solar wind then follows the magnetic field up to the north or south poles and then hits the atmosphere. And that's the part we care about here. Once it hits the atmosphere, it ionizes and it gives off some light. And that light is the northern or southern lights. So that's that interaction that we get there. And then the atmosphere warms the surface through the greenhouse effect. And a lot of you, I hope, have heard of the greenhouse effect before. But if you haven't, again, because I really don't want any of this taken down for licensing issues, otherwise I would have played the clip. If we were in a classroom, I would have played the clip. But the Futurama episode Crimes of the Hot starts out with a great old-timey style science film that explains how greenhouse gases work. And the greenhouse gases are these mobster dudes here, and then the sunlight comes in, hits the earth, and then when it tries to go on its merry way, it gets beat up by the mobster dudes and the dead bodies of the solar radiation get trapped around the surface. Now, that's a cartoony, quick, easy explanation of the greenhouse effect, but what it really is, remember when we... And again, I keep saying remember. If this is your first time here, no worries at all. We've talked about this before. If you're interested in learning more, there are past videos. You can find them on here or on my YouTube channel. But we talked about thermal radiation of planets. The fact that the sun hits planets and then that sunlight gets radiated off. But with greenhouse gases that are present in the atmosphere, what happens is the sunlight hits the earth and then the earth radiates heat in infrared, right? Predator heat gives off infrared radiation. When those infrared photons are trying to leave, greenhouse gases absorb infrared radiation and then rescatter infrared radiation. So it's not able to leave. And the more greenhouse gases you have, the more molecules there are present that will absorb that infrared radiation. So it gets harder and harder for that heat, those infrared particles, to actually leave the atmosphere. If there's a lot of greenhouse gases, it'll just keep absorbing and re-emitting infrared radiation, which is heat. I hope that makes sense. That was one of those things that kind of clicked a little bit later than it should for me. But, sometimes it takes a while for that sort of stuff to sink in. So that's how greenhouse gases work. They trap and re-radiate heat. And depending on how much you have in your atmosphere, that will dictate how much of it is trapped. And, yeah. All right. So talking about the global average temperature, just when we're talking about planets in general, when you're saying, all right, what's the average temperature of this planet? It dictates both from the distance from the sun and the reflectivity and also the greenhouse warming effect. Yeah, Cairo, exactly. Humidity in our atmosphere keeping us cozy and warm. All right. Cozy and warm. Sometimes. So the distance from the sun radiates heat and light that's going to go down the further away you are from it. And so it's going to be colder the further you are away. And the reflectivity of the planet is also called its albedo. So a high albedo will mean not what you think it means, but mean that it's very, very bright and that it reflects a lot. This really comes into play with like polar caps, sheets of ice, because ice is really reflective. And so that when we say it's reflective, that means those photons hit and they bounce right back off again. That's reflected. So it's not absorbed. It's not converted into anything else. It's just reflected off. And so because of that, that affects the temperature. The more reflective you are, the cooler you're going to be because you're not able to absorb. So equivalent of wearing a white shirt on a sunny day versus a black shirt on a sunny day. You're going to have different reflectivity, and that's going to affect the temperature. But the greenhouse warming actually has a big, big impact on the global average temperature, particularly talking about Earth, because, yes, Cairo mentioned we experience our temperature here. We have some concept of what it is. If Earth did not have greenhouse gases and didn't kind of trap its heat a little bit from the atmosphere, if it was just how far away from the sun we are and just how much we're reflecting, our global average temperature would be just about, I think it's 0 C, I want to say. I think it's, no, 0 Fahrenheit, sorry. So not freezing water-wise, just freezing person-wise. I would not be comfortable in that. So yeah, it's about 0 degrees Fahrenheit. So it's cold, and that's what it would be without our atmosphere. So our atmosphere is good. However, just, you know, if we did a whole segment on climate change, which I think is important and something that we should all learn about and understand, that would be the entire class today, which is not what I want to do. But it is important to understand that the increased greenhouse gases are trapping more and more heat, and our global temperature is going up, and it is caused by humanity and manufacturing, and it's irrefutable data on that. So we don't have to get into that debate now. We can get into that debate later if you want. I don't have any, like I said, it could be, we could talk about it for the whole hour, and I want to teach some astronomy, but it is important. Please learn about it. If you're curious and you're really not sure, reach out. I'd be happy to talk to you about it. I have no problem having those conversations, but I want to teach astronomy right now. So talking about the atmospheric layers, I apologize for the picture because I just took this picture myself. But the atmospheric layers, as far as we're concerned at the astronomy level, so this is not like meteorology, atmospheric science discussion level here. We have these 4 layers, which are then flipped around when we're going bottom up here. So it's starting from the ground and going up. We have this troposphere. And the important part here is that based on what these layers are made out of dictates what the temperature gradient is and what electromagnetic spectrum it's absorbing or allowing through. So when we talk about our troposphere, the part down here, this is where greenhouse gases live. And as you get higher in elevation, the temperature decreases. And we kind of know that intuitively, right? If you go hiking, it gets colder as you go further up. And then as you transition into the stratosphere, and then this little part here where it seems to make an elbow and go this way, this is also called a mesosphere, but we're not worried about that. So we're not going to talk about that right now. But the important thing with the stratosphere is that you see that it starts to heat up as you are going further and further up, which is super counterintuitive. But that's because the ultraviolet light gets absorbed at the stratosphere level. And because we're absorbing this higher energy light, this ultraviolet radiation, that's heating up the atmosphere. Another way to think about this. Remember that temperature is based on average kinetic energy of particles. This is what we talked about when we did sort of the physics classes. You go down to sort of the molecular atomic level. That movement and that vibration of those atoms and molecules is what creates that thermal energy. It's really the kinetic energy of these molecules just moving around. That's heat. So because we're absorbing ultraviolet radiation here, there's more vibration and it's heating up as you go up. Then it starts to transition and cool down where it's not absorbing that ultraviolet radiation. Then we get to the thermosphere. And so now we have X-rays and ultraviolet heat are heating up and ionizing gases. So there's even more energy being pumped into this here. So this is where X-rays are mostly absorbed. And then the temperature does start to drastically increase the higher up you go. And then we get to the exosphere. The exosphere is basically where you're just starting to lose atoms and molecules just because they're so far out. They're still mostly trapped by gravity. You know, the Earth's gravity, the planet's gravity, is keeping these atoms and molecules where they are, but it's very easy for them to escape. So if they're fast, if they're heated up, if something happens, then they'll fly off, never to be seen again. And we'll talk about that process here. So how atmospheres can gain or lose gases, and it's okay to get really giggly here because outgassing is still one of my favorite things ever. I had to do an entire satellite discrepancy report one time on unexpected outgassing, and I could not make it through the day without giggling. So it's okay to have an immature sense of humor sometimes. So sources of atmospheric gas, exactly. Sources of atmospheric gas, how we add atmosphere is through outgassing, but through the through volcanism, right? Letting gases that are trapped under the surface go out of the surface. I highly recommend you start using outgassing in your everyday language because it's hilarious and it's fine. So I highly recommend it. I think it's funnier than Uranus. I'll just put it that way. Okay, and then we get evaporation and sublimation. So this is, ices just evaporating. Sublimation is where you go from a solid directly to a gas. So sometimes when light hits ices, that will, instead of melting them and going through the liquid phase, they'll turn directly into gas, and that's what sublimation is. And then the liquid to gas phase is evaporation. And thank you for the follow, Pepper Cat. Happy to have you here. Thanks, Brad. Yoga is a leading cause of outgassing. You're not wrong. And then surface ejection. This is when like things hit the surface. And so, for example, if you, and this is kind of talking more about the other terrestrial planets, not so much Earth because we have such a relatively thick atmosphere. Not a lot of stuff can make it through to do this. But if we're talking about Mercury and Moon, when meteors hit the surface, that will eject material. And sometimes that energy can split apart the molecules. Sometimes it can expose pockets underneath the surface. And that's what that surface ejection is. That's starting to add more stuff into the atmosphere. And, well, that's literally, okay, for those of you who haven't seen the episode, watch that Futurama Crimes of the Hot episode. Because all of this, when I taught Astronomy 101, we just watched the entire episode because it was like the Earth was getting too hot. They have to figure out ways to move. Robots give out a lot of gas. They all outgas in a certain... It's hilarious. Okay. Inappropriate jet assist. I like that too. Okay, so let's talk now about how you can lose atmospheric gas. Condensation, remember that's the phase transition going from gas to a liquid form or a solid form. You're losing the gas. And or chemical reactions, just how the interactions that you have sometimes will form molecules that will no longer be gas form. Solar wind stripping, so this is as the solar wind is hitting our planet, it basically brushes off particles, and that's kind of where you're talking more in the exosphere side of things. And then just thermal escape. They're heated up and they get more kinetic energy and they take off. So that's kind of, again, the exosphere type range where just because of their motion, if they're heated up, they're moving, so they have some temperature, and then that motion, if it's high enough that they're able to escape the gravitational pull of the planet, that's what we call thermal escape. So those are the ways that an atmosphere can gain or lose gas. Let's start talking now specifically about the geology and atmosphere of the different objects in the inner part of our solar system. Buy one, get 16. Yeah, so are these processes approximately in equilibrium on Earth? I would say yes, and approximately in equilibrium for most systems that will... that have a stable atmosphere. So I say stable atmosphere. So that's things like, when we talk about studying planets that are losing atmosphere at a rapid pace or they wouldn't really gain atmosphere at a rapid pace. You mostly would gain atmosphere at a rapid pace early on in the solar system's formation. But once you reach that stability, whereas like right now, our planet's been around for 4 billion years with the rest of the solar system, we have some level of equilibrium here. That we've settled on. And but as the atmosphere starts to heat up, those processes will change. Again, it's a little bit of the time scale too that is hard for us to wrap our head around. In astronomy, saying like, oh yeah, we're trending toward losing our atmosphere, for example. Not saying that we are, because I don't know what the numbers are exactly, but that could be hundreds of thousands of years, right? So for us, it doesn't necessarily matter that much. But yeah, thanks for the question. Okay, so remember last week we talked a little bit about just general geology, and I'll kind of come back and reference some of it here. I'm going to go and talk about the Moon, Mercury, Mars, and Venus, and we're going to do the geology and the atmosphere of them both as we go through. So this is a very, very, very pretty picture of the Moon We like it. This is the near side of the moon. But talking about how they formed. So these are what we call mare, or basically seeds. Seas, not seeds. Seas. And this is a great depiction of how they form, how they look the way that they do. And lunar maria, that's it. So here we have basically a projection, not projection, progression. It's been a week. All right, progression through time. We have this surface here, it gets hit, it gets bombarded, we get a big crater. When that crater happens, remember sometimes we can expose parts beneath, and it's also heated up because we have this big impact that's transferred some energy. So when it heats up, then it becomes molten, and then when it cools off, you get left with this sort of magma type rock that's left behind. And that is primarily from these impact craters. So what we see, the lunar maria, especially recent ones, like these ones that don't have any craters on top of them, right? You can just look at this image and kind of age every portion of it separately, right? You can say down here is the oldest, here is younger, and here is younger here, because this got hit by a crater after this had already formed. So there's different like things you can do with that. That's planetary geology. A lot of that is this sort of detective work to piece this information together. But some of you may have heard the term, and I just use it here, the near side of the moon versus the far side of the moon. The key with the moon is that it's tidally locked with us. So what that means is as the moon goes around the Earth, the same side faces us the whole time. This has nothing to do with the phases. I mean, if you remember, like 10 weeks ago, we talked about the phases of the moon and how that's caused by the different angles that the sun is hitting it at. So that just determines what part is in shadow. But the side itself that's facing us is always this side. It's tidally locked. Before I continue with that, Cairo is asking, is the Sea of Tranquility violently formed? I mean, that's an excellent point. And I don't know specifically about the Sea of Tranquility, but I do like that comparison. And I would say yes. But the big question here is like, okay, if we were just talking about like this, right? That you have this sort of nondescript surface with a lot of crater impacts, and then over time it starts to look like this. Why don't both sides of the moon look the same way? Now you can still see like over here on the far side of the moon, and this is done through imaging. So this is not a picture taken from Earth because we never see this side of the moon from Earth. You can actually kind of, if you're able to see the resolution on your screen, you can actually see these strips that built up this image as the imager was orbiting around the moon. Oh, thank you for the follow, Quintus. And but this far side of the moon still has some of those seas. God, what are they? Maria. Whew, that's my word mental block for the day. Apparently, it still has some of that Maria there. And yeah, I mean, Andrew, it is hard to wrap our minds around. I think that there's a lot of things in astronomy that are still difficult to just conceptualize because it's counterintuitive. And so the idea that it's tidally locked is kind of hard to image, and you just kind of have to do this. And then I've seen some great demonstrations where, you can look top down, and I think we showed this back in my, where we talked about the phases of the moon, where you can see that the moon itself is rotating, and it's just the way that it's rotating around the Earth, it matches its orbit. But the question is, why does it do that? And why does the near side look so much different than the far side? And a lot of that has to do with how the moon formed, how we think it formed. And we've talked about this a couple times, especially a couple weeks ago when we talked about the formation of our solar system. But the idea of how the moon formed, particularly because it's such a unique object, it's so much bigger and relative to the size of the Earth. If you think Mercury and Venus don't have moons, Mars has 2 tiny potato-shaped moons. Earth has this huge honkin' moon around it. So the idea is that early in the solar system formation, where we were starting to get these planetoid things forming, Earth was forming and it was coalescing and it was grabbing a lot of stuff as it was going, but it was very hot and dynamic and mostly come together. And then something hit it. And when something hit it, it tore off a chunk. And when it tore off that chunk, that stuff was also kind of hot and dynamic. But it got trapped into the gravitational pull of the original planet. That original planet being Earth, this being the moon. And because they were both hot and molten, particularly this, which had been violently torn away from the parent planet, it cooled off. But as it was cooling off, it was pulled toward the Earth. So essentially, all that molten magma on the inside was pulled toward the Earth. The liquid stuff was more gravitationally distributed towards the Earth than it was the far side. So all that magma was pulled toward this side. And then as it's been exposed, or even just as it was cooling off, then it solidified on that side. So that's why we have more magma on our side than you do on the other side, because during its formation, all of that molten magma was pulled towards the Earth's side, and that's why it's mostly exposed. I hope that makes sense. Again, this is one of those things that's a little hard to describe in this format, where I don't have a classroom that I can jump and dance around. Do demonstrations. But yeah, so it's important to note the moon is tidally locked. The same side faces us all of the time. But the tidal locking also, it's not that that explanation of the formation just explains these Maria. It also explains the tidally locking. Why that same face stays facing us the entire time has to do with that model of the formation. Okay, so let's go to Mercury a little bit. Now, Mercury is weird. Mercury has a very large core compared to its overall radius. If you look at the other terrestrial planets, Mercury's got a very, very big core compared to the rest of it. And the thought is that Mercury has cooled off and it's shrunk as it's cooled off. Now, I'm not talking about its distance from the sun, getting hit and radiated. I'm just talking about the interior of the planet has cooled off. Possibly from some bombarding, possibly just from the size of it. But as it cooled off, this is the cool thing, it's basically formed wrinkles. So I'll try to picture this a little bit. You're starting like this, and as you shrink, it's got nowhere to go. So you get these formations here as well. And yes, it is. So let me double check that statement, because that sounds right, but I don't have that fact stuck in the side of my head. As it were. I don't have any note here. So someone can look it up and just say, is Mercury tidally locked? Or I can look it up at the end of this. But there doesn't seem to be any current sort of tectonic formation that's happening, or there's no active volcanism on Mercury. It's just started to cool off. The core and the mantle kind of shrink down, and then portions of that crust were forced under each other, and that's where you get these like wrinkles on the surface as it cooled off and it shrank, which is pretty awesome. And this is just a baller picture of the surface of Mercury. And usually Mercury and the moon are kind of lumped together because they have very little atmosphere. You might be right, domestic. We'll confirm that after this. So the atmosphere of the two of them, this is like atmosphere, right? It's really just that exosphere. So remember, we talked about the layers of the atmosphere. That very top layer is what we call the exosphere, where particles, if they get enough speed, can just boogie on out of here. That's pretty much what we have with the moon and Mercury. They have an atmosphere in the sense that there are gas molecules that are trapped in the gravity of these objects, but it's like 0.00001%, if that. Even that seems like a lot. We have this discussion in the Discord. I think Todd put in like 12 zeros or something. It's very, very much different. So, but this image is really cool. This was another one that I just took out of my book. But these sizes are actually relative to each other. So this is the moon and this is Mercury, and that's kind of how big they are compared to each other. And because Mercury is so much closer to the sun, you can actually see that exosphere. All those little particles, it has this structure because the sun is over here and the sun is pushing those particles off. So you get almost this tail as it's escaping through there. And then the moon is much further away, so it doesn't have that same effect. It might have a little bit of it, but you still have these individual gas molecules that are trapped around just gravitationally, and they may get enough speed or radiate that thermal radiation escape just so we get here. Thank you, Benny. I appreciate it. Ooh, Michael looked it up. Radar observations in 1965 proved that the planet has a 3-2 spin orbit resonance, rotating 3 times for every 2. I love resonance. And thank you, Benny. Same thing. Awesome. Relative to the fixed stars, it rotates on its axis 3 times for every 2 revolutions. Math is beautiful. All right. So again, Moon and Mercury mostly have, their geology is mostly made up of impact craters at this point. We also have some shrinkage, as George Costanza would appreciate, of Mercury, which has caused these cliff faces, these wrinkles that we get here. Ooh, domestic, that's a really good question. Does any of the atmosphere that leaves Earth get captured by the moon? I mean, it's possible. I think that it's just, like, there's no reason why it wouldn't. I would probably just err on the side of saying that I wouldn't necessarily claim that most, if not all, of the moon's atmosphere comes from the Earth. I would say it more comes from the impacts that send up gas into the atmosphere. So, oh, so big fun art. Okay, thank you. So the majority of Mercury's surface was stripped off by, so that is, I didn't really go into it that much. That's why we started with a much bigger core relative to the overall radius. That during the formation of the solar system, I think that's one of the models. Another model was like maybe that there was just a big impact that stripped off some of the outer layers. But regardless, that was more in the formation that just left behind a more massive core. So again, similarly to how something hit Earth near the final stages of Earth's formation, something hit Mercury or the gravitational pull of Venus as it was forming and clearing out its orbit, pulled material off. Both are models for how the core became to be such a big proportion of the radius. Then we go into this explanation of, okay, now that we have that big core, that still is cooling off and it shrank and then caused the shrinkage. Okay, so that's the moon and Mercury. Ooh, this is probably going to go longer than 40 minutes. That's okay. This may end up taking the whole hour, but that's all right. No worries. All right, let's go to Mars. Mars is awesome. I love Mars. This is just kind of a cool layout flat map showing where we've sent little robots to go check out areas. And you can see where Perseverance is going to go and where all the other 2 objects have gone. And I think regardless if, Opportunity we've lost contact with, it may just be establishing its own mutant territory robotic colony in this section of Mars. So just be prepared for that. Okay. That's a deep reference to an XKCD comic about how the fact Opportunity lasted so much longer than it was supposed to, and it ends up colonizing like most of Mars. So I love the geology of Mars. We're gonna come back to like what this hot nonsense is, but the big the features of Mars. Oh, J3Z, thank you. Are this one, Hellas Planitia. Then over here we have the, if this was a class, I would have us all say it out loud. Ready? 3, 2, 1. The Tharsis Bulge. Because it's just a hilarious word as well. The Tharsis Bulge is on this side. And this is Olympus Mons over here. We have 3 more volcanoes here. These are all big, huge, but broad shield type volcanoes. And then here we have Mariner Valley, or Valles Marineris. So those are sort of the bigger features of Mars. Like your must know. If we were doing an exam, that would be list 3 major features of Mars. The Tharsis Bulge, Hellas Planitia, and then one of the other ones. All right. So that's sort of the general geography of Mars. is interesting. Obviously, it has a lot of history to it. We can see evidence for volcanism. We can see, dead volcanoes here. Massive dead volcanoes. We can also see like a huge crack in the surface that doesn't necessarily look like the Grand Canyon, in the sense it doesn't appear that erosion is what caused a Mariner Valley to form. Yeah, there you go, Cairo. Or maybe was she named after Mariner Valley? Ah. All right, so Valles Marineris, that's this big crack here. And, but there's evidence of volcanism, there's tectonic activity, regardless of what caused this. There's indications of tectonics. And then we obviously, especially on this side, have a lot of impact craters. The cool thing here is also you can see how much flatter this side is. That's more formed from the fact that there was volcanism. That, remember we talked about how that volcanism can shape the surface of a planet by basically covering up the layers. So stuff, you get these impact craters, but then a volcano goes off, and especially these shield volcanoes, all that magma is going to smooth out the surfaces. And so that's kind of what we're seeing here. And that indicates that these volcanoes were relatively young compared to the overall age of, or they at least remained volcanic for a long period of time, up until recently. Okay, one of the other features that we can see on the surface of Mars is evidence that there was water on the surface. So this is some evidence of water flows on the surface of Mars. This was sort of the first indication that we had. So when we first started looking at Mars, we thought that it was a lot like Earth. And I just mean through crappy old Galileo-style telescopes. Not crappy, that was mean, but you know what I mean. When we started looking at Mars, what we saw were, and I'll go back to this, we saw these dark patches. These dark patches here through a telescope just looked like oceans. So society thought that Mars was just like Earth, and that's where the idea of Martians came from. They thought that it had continents, oceans, that it looked like Earth because of that. And, ooh, that's cool, Andrew. I'll check that out. But then we went there, and and telescopes got better, and we visited, not humans ourselves, but we sent stuff there, took pictures, realized there is no water on the surface. That made us have a sad. But we have found evidence that there was water on the surface at one point, first indicated by by this. And, oh my God. I forgot the word again. I should have put it on here. I got cocky. I said I wasn't. Okay, first of all, we had the water flows. Then actually Opportunity discovered something called, it's a geological term, but blueberries. Essentially river rocks, I think is kind of a good comparison for that. That these, thank you, Benny. Thank you. You remembered. You knew what had happened. You saw the connection fry. So these river rocks, these blueberries that Opportunity saw were again an indication that there was water on the surface and that there was water flow on the surface. And then thanks to Benny reminding me, but Curiosity found sedimentary rock, and that's what we're looking at here. So we see the sedimentary rock, these layers, particularly this. I mean, this is amazing. This is evidence not just that there was flowing water on the surface, which was everything else, but there was standing water on the surface, that we had these lake beds. Curiosity is in Gale Crater, which was a good candidate for like, oh, it's a big, deep, shallow area. Big, wide, not deep and shallow, but it looked like it could, if there was water on the surface, it would have pooled in Gale Crater. And so that's why we sent Curiosity there. And indeed, we found this sedimentary rock. And yes, I did have to check the chat again so I can remember what it was. And what that is it basically shows, okay, you have water there. It deposits layers of rock. And then that water, there's more erosion, there's more wind, blows the dust in, all that rock settles again. And you just have this repeated settling of layers, and you get sedimentary rock from that. So yeah, I mean, that was a lot of that reasoning. And then indeed, that's exactly what we saw. So we know that there was water on the surface of Mars, and we know that there was water for a long period of time on Mars. So thank you, Curiosity. If you ever need a boost, Google Curiosity selfies. You are not disappointed. And all right, so what's the weather atmosphere like on Mars? And then we're going to talk a little bit about what happened to the water, because that's an important component of the atmosphere as well. You may have heard of dust storms on Mars. They can be bad. They can last for a very long period of time. So, yeah, you're not wrong, Roger. That's a good point as well. The issue is with the surface of Mars, there's a lot of oxidation. It's very rusty. That was sort of that chemical process I talked about earlier. That's oxidation. And that dust can be the consistency of like baby powder. And the gravity on Mars is only a third of what it is on Earth. And the atmosphere right now is only 0.6%, so 0.006 times what Earth's atmosphere is. Yes, and domestic, I'll get to that in a second. But how it is right now, it's only 0.6%. It's very, very, very thin, but it's not non-existent. It is there, and we do get dust storms. This is another Curiosity selfie, but you can actually see the dust storm behind it. This is the dust storm that covered up Opportunity solar panels, resulting in the loss of contact from Opportunity. And yeah, so these dust storms do happen, but it's important to note, and if you watched my episode club about the Martian, because the atmosphere is so thin, when these dust storms happen, they kick dust up, but that dust doesn't actually, you don't feel the wind, because we feel wind from the pressure of atmosphere pushing on us. Mars doesn't have a thick enough atmosphere to actually push us or knock over, you know, a rocket or blow a satellite into Mark Watney. It kicks up this really, really thin dust, and then it takes a long time for it to be settled down. And yeah, Roger, that's a great comparison. Our atmosphere at 45 kilometers, which is really, really high, is about equivalent. So that's a great point. And then there is some cycles of weather on Mars as well. This is an animation of the North Pole on the left and the South Pole on the right over the course of a year. So there is sublimation and condensation that happens. Remember, this isn't raining. This isn't melting into liquid. This is just a solid evaporating into a gas. This is dry ice. This is carbon dioxide primarily. And it evaporates, and then it condenses and goes back down. Okay, so what happened to Mars? And Domestic kind of hinted toward this a little bit. We know that there was standing water on the surface of Mars. Because of that, there has to be an atmosphere. Atmospheric pressure is what allows water to remain in liquid form. If you've done this experiment at a science museum where you can put a little cup into a vacuum jar, suck all the air out, the water will start to boil. Not because it's hot, because there's no atmosphere holding it down and keeping it in liquid form. So in order to have liquid water on the surface, you need to have an atmosphere that is thick enough that it keeps it in liquid form. And that had to have been the case for Mars. Now, what the atmosphere is right now would not work. If we took a cup of water out onto the surface of Mars, it would boil away. It would evaporate. So that means if there was liquid water on the surface of Mars in the past, it had to have had a thicker atmosphere. And this is something that the Messenger spacecraft is going to study, that is studying right now. That it is studying what happened to Mars's atmosphere. It's trying to study the proportion of the atmosphere, really get a lot more detailed readings on the molecular distribution to see if the atmosphere slowly disappeared over a period of time or if it was like a quick impact that caused a lot of it to disappear. And when I say impact, that's what we're talking about here. Now remember, in order to keep an atmosphere, you need to have a magnetic field. This is all tied together. And that's what we talked about last week, how a planet can have a magnetic field. It needs a molten metallic core. That molten metallic core, as it rotates, gives off a magnetic field. That magnetic field shelters the atmosphere from solar winds blowing it away. And that atmosphere will keep liquid water liquid on the surface. So it's this whole cat that ate the rat chain. You need a magnetic field to protect the atmosphere, to protect the liquid water. Yeah, and Cairo said you'd either need enough atmospheric pressure or something above the water, like ice. Yeah, I mean, that's fair. I mean, exposed surface water, absolutely. And but the question is, so what happened? What happened to that magnetic field? What happened to the core of Mars that caused that to happen? There's two theories. One's more apocalyptic than the other. That one I like the most. But the one that's, I guess, because there's no evidence, there's no direct evidence. We didn't see it happen. One of them is, okay, Mars is half the size of Earth. Just cooled off. It just like Mercury. You know, Mercury cooled off, Mars cooled off. The interior just solidified, and it lost its magnetic field. Because it's half the size, you take 2 loaves of bread out of the oven, one half the size than the other. The one that's half the size is going to cool off faster. Once it cooled off, that magnetic molten core solidified. No more magnetic field. Atmosphere goes away. Water evaporates. I like my theory better. It's not just mine, but this is Hellas Planitia. This is the Tharsis Bulge. Hellas Planitia is an impact crater. This is a massive impact crater. It's the largest visible crater in our solar system that we've seen. Its crater has craters, and those craters have craters. So this crater here is almost directly opposite from the Tharsis Bulge. So the Tharsis Bulge, we think, is caused by an impact crater hitting here and bulging out the other side. Like, brutally, causing a crack, causing massive volcanic activity that then also completely disrupted the magnetic field, completely disrupted it. That disruption caused it to just become unstable and solidify off a lot faster. Solidified, magnetic field disappeared, atmosphere went away, water evaporated. So those are the two kind of big theories for Mars. And it's awesome and cool and exciting. Okay. Now, and yeah, Roger, actually, that's a really good point, too, that might also have started out with fewer radioactives. And, yeah, everyone's sharing their sad astronomy experiences that were ruined by weather and clouds. It happens. All right, now we're just going to wrap up. We're pretty much going to go the whole hour, so I apologize for that. We're going to wrap up with Venus. Now, I could talk about Mars for a lot longer because it's really cool, but I wanted to end with Venus just because I have something really geeky and adorable and amazing to talk about with Venus. But this is, again, kind of blown out picture, flattened out picture of the surface of Venus, mostly taken through radar images. Not mostly. Yeah, Roger, that's exactly something else that they're going to study. That's, I think, what Curiosity has been taking core samples. Remember, Curiosity has like that mole thing. And then I think Perseverance has the same type of instruments. So taking these core samples, trying to study what the interior looks like will give us clues to that history as well. It's just an unknown. We really don't know. So that's something that we're still studying. All right, with Venus, looking at the surface of Venus, these are the Venera landers that actually made it through the atmosphere. The atmosphere of Venus is a unique beast. So, these are pictures of the surface of Venus. High volcanic activity. I feel like there was something else I was going to say about Venus that I don't remember off the top of my head. Huge amount of volcanic activity, large amounts of outgassing. Our favorite word. And yeah, I think that was a major thing. Let me see if there was anything else. It's really the atmosphere that's the important part with Venus. Yeah, the hell planet. Agreed. The atmosphere is really what screws us up, because Venus is about the size of Earth. It's almost 1 g. I think it's like 0.9 g times the gravity. So, like, we could walk around on the surface of Venus pretty well, except for the darn atmosphere. Breaking out these layers again, you can see right here, this is 90 times the surface of Earth. So this is the atmospheric pressure 90 times, 90 times. If you took the column of air above me, added all that up into a weight, about the weight of a car, now turn that into 90 times. That just squishes you. Yeah, and Roger, a lot of the imaging actually is mostly because of the clouds. That's why we needed the radar. It's got really, really thick clouds, and it's sulfur. Mostly sulfur. Not pleasant. Not good for us. Sulfuric acid in the atmosphere. High amounts of sulfuric acid. Huge amounts of carbon dioxide. Very, very, very high temperature, high density, high atmospheric pressure. Because this pressure is so high, the temperature, yeah, it's actually, thank you for that. I did have that number. I have that number. Just give me 1 second. For how deep you would have to swim to get 90 times the pressure. I think it's about 1 kilometer under the surface. So, yeah. Yeah, it's not ideal. And, yeah, you'd have to go about 1 kilometer under the surface of water to get that same atmospheric pressure. Not pleasant. Not ideal. And, yeah, 0.6 miles. So, yeah. The temperature, so it's more the temperature is just too high. Not so much because when we talk about the Goldilocks zone and the temperature, I think Venus is technically a little too close to be warm, but its atmosphere is highly reflective. So I think that cools it off as well. Yeah. And that damn atmosphere collapsed the first few landers we tried to actually send to image the surface. When we tried to throw something through the clouds, not necessarily knowing how dense it was, they just went and destroyed themselves because it was way too stressful. Oh, thank you, Dr. Derp. Appreciate it. Right. Because the pressure is so high, that causes the temperature to go up. Remember, I mean, this is kind of a physics thing. If you increase the pressure, the temperature is going to go up. And so the temperature on the surface as well, it's not, I mean, you could keep it in, like, there's so much atmospheric pressure to keep your water in liquid form, but then it's so hot that it's going to evaporate out. So it's a delicate balance. But the keen-eyed among you may make note of something. Depends how well you know your Kelvin temperature. Average temperature on Earth is about 300 Kelvin-ish. About 288, I think. If you follow this up to where you get 1 bar of pressure. So this is about where Earth is. Does it give anyone ideas? Because it gives me ideas to build a cloud city in Venus. And this is something that has been floated before. So, unfortunately, you can't necessarily breathe the atmosphere because that whole sulfuric acid thing is not ideal. But, yeah, super cool. Super fun to think about. And I love this idea, and I hope that we do it because I want a cloud city. We talked a little bit about the greenhouse effect before as well. Venus has something we call a runaway greenhouse effect. So earlier we had a question about the equilibrium with atmosphere. The amount going into it is the amount leaving it. The Venus, when it comes to the temperature, is what we call a runaway greenhouse effect, where we have, especially on the surface, it's continually trapping air. It's continually trapping heat. I talked at the top about how greenhouse gases work, the fact that they absorb infrared radiation and then re-emit it, and the more of those that you have won't let that heat leave, then it just gets hotter and hotter and hotter. And then as that heat increases, it's going to evaporate, it's going to split more molecules, it's going to create more greenhouse gases that are going to trap more atmosphere, and so it's this runaway effect. And so it's really important to think about. So if you'd like to learn more about this stuff, I can recommend the Futurama episode, Crimes of the Hot. High recommend. Also, if you can find it, I don't know if it's on Netflix still, but the new Cosmos, the Neil deGrasse Tyson Cosmos, has a great episode on Venus, greenhouse gases, climate change, the difference between climate and weather. And I would say as well, you know, I said that we weren't going to take the whole hour to talk about climate change here on Earth because that's a whole other conversation, but it's an important conversation. So if you aren't sure, if you've been confused, if you're not, you know, if there's a lot of information that you're being bombarded with, that it just feels like everyone has their own agencies and you just don't know where to look to get an answer, I highly recommend the Neil deGrasse Tyson Cosmos about Venus. High recommend. Okay. Yes, it does. And it's got some great imagery. It's got some great sort of analogies. It's really good. I actually showed that episode again when I was teaching, just because I felt like they explained it and they had a lot of great visuals that helped drive the point home while learning a lot. So, oh, that's cool, Cusco. And yeah. All right. We are at the end of the hour. That took the whole thing. So I will hang out for a couple more minutes just to hang out with everyone in the chat as a thank you for being here. Oh, and thank you. I love my shirt too. But if you're watching this after the fact on YouTube, don't forget to like and subscribe, and you can catch our live stream on Fridays at 1 p.m. Pacific time on Twitch. The link is in the description below. And thank you for being here. Feel free to leave any questions in the comments below as well. So thanks, and we'll see you next time.